Hello, in today's video we're going to discover and apply our idea of rotational inertia and rotational kinetic energy. We will be using a practice exam problem you will commonly see in physics exams, and will show a deep understanding of this concept if you can follow along. Now imagine we have an inclined plane with a angle and a horizontal as shown in front of us, a solid sphere of a radius r and a mass m that's initially at rest of the position shown, such that the lowest point of the sphere is at the bottom of h above the plane. The sphere is released and rolls down without slipping. The moment the inertia of the sphere is about the axis is center. Express your answer in terms of m, r, h, g, h. And we also need to note that initial energy is equal to 2/5 mass times radius squared. Now let's continue to our next page. So we're going to start by finding the transitional kinetic energy and its rotational kinetic energy. We know what those equations are, if you can recall from before. So we'll start by writing out what we know what that means. Like what is transitional kinetic energy? We know it's just kinetic energy from before. When an object just moves in one direction, it's 1/2 mass times velocity squared. Pretty simple, but as we noted before, velocity is an unknown. We can find our velocity using the work energy theorem, because it will leave us with just velocity as our unknown. We also will be solving the rotational kinetic energy as we go, since it will be a lot easier to do both at once instead of separate. So let's get these two equations to be the same, because if you look at our work energy theorem, we know that the potential energy from gravity is equal to the rotational kinetic energy plus the transitional kinetic energy, and these both need to be in the same units if we want to add them together. So kinetic energy equals, we're going to write, if you remember, I equals 2/5, and then it's going to be mass times radius squared. And then we also need to substitute our rotational velocity, which equals velocity over radius. And we know it's squaring these variables, so we're going to get velocity squared over radius squared, which these two will cross out, which will just leave us with our rotational kinetic energy equals 2/10 mass times velocity squared. This will give us the same exact units for both of those, which is what we want. So we know potential energy of gravity is the mass times g times the height, which is a work over displacement, a force over a displacement. Our displacement is h, mg is a work or force. And then so it's going to be set it equal to, and then we're going to write 7/10 once we add these together. Now we're all left with is solving for velocity, which will be pretty easy. So we'll get 10/7 gh equals velocity squared. And now we can substitute out our velocity squared to give us what we're looking for. So we're going to write the kinetic energy of the transitional is equal to 1/2 mass, and then we're going to write 10/7 gh. And now we just need to simplify, so it should look something like this, mgh, and then we'll simplify one more time to get a clean answer. So we're going to divide these by 2, right? So it's going to be 5/7 mgh. Now we're going to find the rotational kinetic energy by substituting in our velocity squared, which is going to be mg, then we write 10 over 7 gh. And look at that. It seems like we're gonna get after we do this, it's gonna give us 20 over 70, which is just gonna be 2 over 7. So we'll finishalize or simplifying. So this will give us 2 over 7 mgh. So yeah, that's it for our first question. We've determined the transitional kinetic energy, and we determined the rotational kinetic energy of our ball. Now we're going to move on to the next problem, where it wants us to find the linear acceleration of the object. So we're going to erase all our work up here, and then you ask the question, where do you get our transitional acceleration? Well, we know the object's accelerating. If we look at our object right here, it should be accelerating in this direction at an angle to its gravity. So let's say this is whatever this variable here, and we know we can get our acceleration from our Newton's second law. So the sum of all forces equals mass times a, and that's how we're going to get our acceleration at first. So we're going to have to do a free body diagram to find the sum of the forces. So let's start by doing that. So we start with a dot in the center, and we know the ground is pushing up on our ball. That's our normal force. There's a force that's pulling it back, which is our friction. Friction normally always points upwards when the ball is running, like it points upwards, the mountain. And then we have our gravity pulling down. Those are our three forces. Now we need to break gravity into components. You can always tell when on these slopes where the angle is going to be from mg to the whatever direction. Just imagine you have this theta here, and as you go to 0, how does it change? Where does it go to? And we know that gravity is going to go to the normal force direction as you decrease your theta. That's how you can get a decent idea if you're on more complex shapes. So we know that this is going to, if we use our SOHCAHTOA, it's going to be mg, and this is going to be cosine theta. I'll write SOHCAHTOA up here so you can get an idea of what we're using. SOHCAHTOA. It basically means sine equals opposite over hypotenuse, and so on. This applies for right triangles. And then we're going to get our force direction arrow, and then this one's going to be mg sine theta. So we're trying to find the forces along the direction of acceleration. So we're going to write the sum of all the forces equals, for the moment it's going to be mg cosine, which is that's what's accelerating downwards. And then we have our friction force, but we don't know what friction force at the moment. Neither do we know the friction coefficient. So that means we have to somehow substitute our friction, but without knowing the friction force coefficient. So we'll have to look at another way of finding this, and we can kind of get an idea that we can get this from torque, since that's the only object that's applying a torque to the object. Now let me draw a torque diagram. So this is your center of mass, and then you have let's say your object radius. And then you have a lever arm, which is the radius of the ball, and then you have your friction force, which is working up the hill. We know that torque is equal to a force times a lever arm and the sine, and we know that the angle is supposed to be 90 degrees, so we can we don't have to write that. So we're gonna do it down here. So we write the sum of the torques equals to the friction force, which is what we want to substitute out. This is going to be static, right, because it's not slipping, times the lever arm, which is just radius r. Now we need to know what torque's going to be. We know that torque is equal to, it's going to be similar to what we, the sum of the forces equal to, which is going to be the inertia times the rotational acceleration. Yep. And now we just need to substitute those two out, since we're not going to be, those are variables. So we know that the I is equal to, or inertia is equal to 2/5 mass times radius squared. And then we know that the rotational acceleration, if we go back to this equation right here, we can substitute it out. So it's going to equal acceleration divided by velocity. Right. So we're going to bring in another acceleration, which is fine since we're looking for acceleration. And then that's going to leave us with our static friction. Now let's cross out this power, and all the radiuses cross out here, and we're going to be left with 2/5 times our mass is equal to the friction static force. Now we can substitute it out. So we're going to write m times a equals mg cosine theta minus 2/5 mass times r. And that's substitute out. And we can tell that the mass crosses out here. This will give us, okay, I forgot the acceleration here. And then we're going to get the accelerations on one side. This should give us around, if you look back here, 7/5 acceleration equals g cosine of theta. And then we're going to get acceleration on its own. So that's going to leave us with 5/7 g cosine theta. And that's how you find the linear acceleration of our object ball here. Now we're just going to circle this so you know what we're looking at. Now our last problem today asks, what is the magnitude of this frictional force we've been looking for? Well, we have a equation for our friction down here. All we have to do is just substitute the acceleration in that we just found. So that's pretty easy. So we're going to write 2/5 times mass, and then we're going to write 5 times 7 g cosine of theta equals our friction force. So that's just going to give us 10 over, let's say, 35. So 25, 30, 35, 35 mass g cosine of theta equals our friction force, which is just going to be 2/7 mg cosine equals our frictional force that's acting on our ball. So yeah, that completes all the problems we're going to cover for today. Thank you for watching my video, and please like and subscribe to motivate me with continuing these type of videos and content.